7, we're going to take a look at distance formula and a couple of other applications of the Pythagorean theorem. One would be distance formula, of course, and then the other one we're going to take a look at a couple of special triangles that are used quite a bit in trigonometry and higher courses in mathematics. But for now, we're going to take a look at the Pythagorean theorem, a theorem that was actually proved about 500-600 years before Pythagorean. So in Pythagorean theorem, so here's what the theorem states. As you can see, it's stated right in front of you. You can follow along with it. So suppose we have a right triangle. A right triangle means it has a 90-degree angle in it. Okay, so if we have in a right triangle, we have the two shorter sides. That would be this side and this side. These are called the legs. Okay, and of course the longest side is the hypotenuse. So with that specifications, in a right triangle, we're looking at the relationship here between the three sides of the triangle. That is, the sum of the squares of each leg is equal to the square of the hypotenuse. Okay, so sum of squares of each side, the two sides, would equal to the square of the hypotenuse. That's pretty straightforward. Now, often when we solve these triangles using Pythagorean theorem, our work involved taking square roots in an equation, and that is why we have this next principle, the principle of square roots. Now the principle of square roots goes like this. If x squared is equal to n, and of course this n has to be non-negative. Okay, so for example, if I have x squared equals to -9, now I cannot square a number and get -9, not a real number. So for that reason we have that we have non-negative real number. Now 9, that would be fine, because the square root of both sides, that would be 3. So but if you have a non-negative real number n, if you're given x squared equals n, then what this principle of square roots allows us to do is to take the square root of both sides. Okay, now sometimes we may write it in this form also. This is another popular form. You go plus or minus square root of n. Again, if you use this shorthand notation for the answer, then there's no need to separate them like this into two separate statements joined with the connective or. Okay, so just to give you a quick feedback example on this one, like I had, let's say x squared is equal to 16. So that means x must be plus or minus square root of 16, or plus or minus 4. And you can try it. When you go 4, you square it, it becomes 16. And -4 squared, also 16. So both of them check. And that's what that principle is. Okay, now let's take a look at an example where we can use the Pythagorean theorem. Okay, so we have this example from your textbook. In this exercise, the question reads, what does it mean to refer to a 51-inch TV set? The reference to 51-inch is the measure of the diagonal of the screen, is what that is. So that means the measure of diagonal means that distance from corner to corner, right? That's what that is. Now, that's what the 51-inch TV means. So here we're given a TV, right? It has a width of 45 inches. So this distance is 45 inches. And of course it has some unknown height, h, that's over here. Okay, we want to know what is the height of that TV if it's a 51-inch TV. Now, something that we could do is, let me actually move this to the side so I can work this one. Okay, so we were given the width is 45 inches, right? That's the distance in the bottom, on the bottom. Now let's try this. Now according to Pythagorean, notice we have this hypothetical triangle here, right? We have this hypothetical right triangle. Right there is where the right angle is. So I can therefore draw this as 51 H and 45, and there you go. Now we can use Pythagorean theorem on this one. The sum of the squares of two sides, h squared plus 45 squared, should be square of the hypotenuse. That is 51 squared. Okay. So here I have set up the equation for us. Next is to actually carry out the arithmetic of this expression, and here I have h squared. Now 45 squared is 2025, and 51 squared is going to be 2601. So if I subtract 2025 from both sides, right, I'm going to get 576. Now square root of 576 is going to be 24 using a calculator, 24 inches. So that is the height of that. Now how did I get 24 inches? Again, using the principle we had here, the principle of square roots. My next step is to take square root of h squared equals square root of 576. Now notice, by the way, according to that principle, when we take the square root, remember we're going to have plus or minus, right? It's right up here. We're going to get plus or minus. So why is it that we don't report the negative and stay with a positive answer here? The reason is because the size of a TV is positive, right? Those dimensions are positive. So it doesn't make sense to say the height of my TV is negative 24 inches. So usually for quantities such as distance, time, things like that, it makes sense to use positive answers. So for that reason, we simply throw away the negative numbers. Okay, and there we have the answer to this exercise. Okay, the next application of this section, which is actually an application of the Pythagorean theorem, is called distance formula. So we're talking about the linear distance, direct distance between 2 points. Okay, not on a curved surface or anything like that. These are in Euclidean geometry, meaning plane or flat surfaces. So, and the distance d between any 2 points is given by this expression, okay, that you see here. And we're talking about this expression right in here. So d is equal to x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Now these subscripts are the coordinates of the first point and the second point. Okay, and that's why they are in the form that they are. So this is like my first point, that's my second point. Okay, now let's see an example of this one. Okay, so to do an example of this one, I'm going to go all the way to number 51 in the exercises. In number 51, we are given a 0.45 and another point is 7,1. Okay, and we want to find the distance between these 2 points. Okay. And in the book, they actually want the answer to like 3 decimals where appropriate. So that means we use a calculator for non-perfect square numbers. Okay. So let's do this. Now initially I need to label these points, right? So I'm going to call this my point 1, this is my point 2. Well, if that's my first point, because I wrote it first, these become x1, y1. And the next to it, that one is going to be x2 and y2, correct? Now if you switch these points, it makes no difference, it works itself out in the formula. Okay, so direct distance between them is going to be x2 minus x1, which is 7 minus 4, you square it, plus y2 minus y1, you square it. And then of course, once we do that, we take the square root of this whole thing, right? And that's what that is. Okay, let me tidy up this thing. Better. Okay, let's pursue this. Now I'm going to take the square root of 7 minus 4, right in here. 7 minus 4, that's 3. 3 squared is 9. So that's 9 plus. And 1 minus 5 is negative 4. Squared is 16. And that would give me a square root of 25, which is 5. So the distance between those 2 points is going to be 5 units long. The units would be the same as units of measurements. Let's say if we were told what these were. Okay, so there's one example. Let's take a look at just one more example of this one. Again, these are not too complicated. Okay, so let's take a look at number 56 actually. Okay, in exercise number 56. So the first point is 521. And the second point is given by negative 31. We want to find again the distance between these 2 points. So the distance would be, remember how we label these? I'm going to carry forward to these x1, y1, and x2, y2 now. So this will become the square root of x2 minus x1 is negative 3 minus 5 squared plus y2 minus y1 squared becomes negative 3 minus 5, that's negative 8 squared, makes it 64. Okay, plus 1 minus 21 is negative 20. You square a negative number, it becomes positive. 20 squared is 400. So the distance is 464 square root of. Now 464. Let's see if we can simplify this one. Okay, 464 is the product of, let's see, I believe it's 16 times 29 times 20. Oops, I don't want to use color. I only use color on perfect square numbers. 16 times 29. Okay, just to make sure. Yes, 464. Okay, now square root of 16 is 4, so that's going to be 4, and then of course square root of 29 remains. This is what we call an exact answer. Means I did not use a calculator. However, we can do an approximation. The approximation means use a calculator. And if I do use a calculator, square root of 29 times 4 becomes 21.541. 21.541. In the book they ask you where appropriate means this is appropriate. When do we know it's appropriate? When this radical is not perfect square, then it's appropriate to approximate it using a calculator. So there you go. That's going to be the answer to number 56. Again, I think it's pretty straightforward as long as you have the formula, right? Which we do. Okay, now we're done with the distance formula. In our next example, we're going to take a look at two very special triangles. Again, these triangles are used extensively in trigonometry and beyond. So let's take a look at the first one. Okay, so again, we're going to take a look at these special triangles. Now, the first of our two special triangles is going to be a 45, 45, 90 triangle. 45 degrees, 45 degrees, 90 degrees triangle. That means this is a right triangle. Okay, now let me see if I can insert the shape here. Okay, so here's my basic shape. Okay, this is a 45, 45, 90 triangle, in that the measure of that angle is 45, So is this one, and this is my right angle. Okay, now let's call these triangles the sides of the triangle. Let's go ABC on these. Okay, now because this is actually a 45, 90 triangle, these are the base angles, this one and this one. In other words, if I put this triangle on its side, on this side, it's gonna look like that, right? Okay, again, this side is now here. Okay, now when I do that, this is my right angle, and this is 45, and this is 45 degrees, and that's what I meant. These are called base angles, and the base angles are equal. Well, if the base angles are equal, then that means, what kind of a triangle is this one? It is called an isosceles triangle, correct? Isosceles triangle. Now, because it's isosceles, that means it has two equal sides. So if one side is A, so is this side. Okay? And then the hypotenuse, we're going to call it C. Okay? Next, I'm going to use the Pythagorean Theorem. Remember, these are the legs, right? These are the legs. Oops, sorry. Okay, so let's apply Pythagorean Theorem to this triangle and see what we're gonna get here. Okay, so that means one side squared plus the other side, the legs, is the sum of square of two legs equal to the square of the hypotenuse. Now a squared, those are two like terms, that becomes two of the same. And then I can take the square root of both sides. And remember, the moment you take the square root principle kicks in, and we have square root of 2a squared. Now, square root of 2a squared, well, square root of a squared is a, and because a is positive, right, in geometry all measures are positive. So square root of a squared is just a, there's no need for absolute value. And 2 remains, and c. Now because we are in geometry, we're going to discard the negative. Okay, so we're just going to stay with the positive answer. And then once we do, here we're going to solve for c. So what did we accomplish here? What did just happen, right? Well, the power of this triangle and the way we derived the formula for the hypotenuse is this. Let's say I have an isosceles triangle. Here's my 45, 45, 90. Okay, and let's say one side is 7. I can actually solve this triangle and find the other two sides. How? Without even going now through Pythagorean. Because these two sides are equal, because it's isosceles, that leg or side must be 7. True? And the hypotenuse is given by that expression. So c is the hypotenuse. Is going to be square root of 2 times a, and this is what a is, times 7. And of course that's just 7 root 2, correct? That's what this is going to be. So the answer is 7 root 2. Do you see that? That's the power of this expression. So all sides are going to have a in them, right? Remember, in the general form, again real quick, I'll erase this in a moment. So it's going to be root 2a. You see that? All three sides have somehow a in them. So we go a, and just put square root of 2 in front of a for the hypotenuse. Okay, so let's take a look at an example of this one. An example, let's try something like, again, let's try. I'm gonna do exercise number 30. Okay, in exercise number 30, we are given an isosceles triangle. This is a 45, 45, 90. How do I know? Because in the book they give you that to be 45. That's all we need to know. That makes this isosceles. We're given the length of one side is 14. We want to find the missing sides. So this other side is going to be 14 also, right? There you go. And the hypotenuse, right? That's C. Remember, we're going to put 14 here, right? 14, 14, 14, and times root 2. There you go. That would be the hypotenuse. And of course, in a calculator, we can approximate, because the question says, where appropriate, an approximation to 3 decimals. So on the calculator, the answer is going to be square root of 2 is about 1.414 times 14. So rounded to the nearest 1,000 is 19.799. Okay, and pretty straightforward, simple. Let's take a look at exercise number 34, which still works with an isosceles triangle, except the difference now is that this triangle is placed in this position. Okay, we're given the longest side now is 8, and we want to find the other 2 sides. Okay, the isosceles sides. So I'm going to call that A. Remember, hypotenuse is when you put root 2 times A, correct? So in fact, here we have an equation now. If root 2 times A is 8, can I solve for A? We can divide by square root of 2, couldn't we? And that would isolate A. There you go. So A is 8 divided by root 2. Now, they don't want radicals in the denominator in these types of problems, so let's rationalize the denominator, something we did in 2 sections back in chapter 10. So multiply top bottom by root 2, and this is 8 root 2 divided by root 2. Root 2 is just 2. And now that we have that, we can actually divide out the 2's, true? Right in here, and so the final answer is 4 rad 2. And again, this is what we call the exact answer. Okay, up here, this is exact. That means we did not use a calculator. Once you use a calculator, then it becomes an approximation. So in number 34, the approximation is going to be square root of 2 times 4. 5.657. 5.657. And that's to 1,000th significant digit approximation to that. Okay, so this is how you would work the isosceles triangles, 45, 45, 90 triangles. And now that we derived this expression, here's what's in your book. The lengths within isosceles right triangles. Again, for an isosceles triangles, these 2 sides are equal, and note they're each A, and the hypotenuse is also A times root 2. So all sides have A in them. True? They all have A in them. It's just you multiply square root of 2 times the A on the hypotenuse. Okay. Now we're going to look at the second special triangle next. The second special triangle that we're going to look at is going to be a 30, 60, 90 degree triangle. Okay. Now to look at this one, let me grab a triangle that's suitable for this work. Okay, this is actually perfect. So I found a triangle that works. Now this triangle is an equilateral triangle. That means all sides are equal. So this side, and this side are all the same. Okay, now for simplicity of our work, to where we don't need to introduce fractions in our work, I'm going to call these not A like the one above, but rather 2A. Okay, so that's going to be 2a. And the next thing I'm going to do is I'm just going to drop the perpendicular bisector of this angle. Now remember, the perpendicular bisector of the angle also bisects the side opposite to it. To bisect is to divide into two equal parts. Okay, now in an equilateral triangle, the other thing that is known, the measure of each angle is going to be, the interior angle is going to be 60 degrees for a total of 180 degrees. Okay. Now, the other thing that we note here is that because we bisected this side, so the whole side, right, the whole thing is 2a. True? That is 2a. So half of it is just going to be a, isn't it? The other half is here. Good. Now what I'm going to do is I'm going to break off this triangle, okay, and only carry half of it. Okay, so there you go. I broke it off, and now I got two pieces here, right? One on the left, one on the right, and actually right in here I have the one piece, right? That's like the right half piece. Now if I label the sides at this point, what they look like, this side is A, the height or the altitude I don't know yet, and the hypotenuse was 2a, correct? So it's right in here. That's what this is, 2a. Okay, now let's actually do this. I'm going to use Pythagorean. Oh, the measure of the angle, sorry, almost forgot. That's your 60 degrees. This is the right angle. Now this should be, remember we bisected the angle, so that's 30 degrees. Okay, now from this I can actually do the Pythagorean theorem, right? Okay, so according to Pythagorean, the square of the hypotenuse is equal to sum of squares of the other two sides. Now we already have, as you can see, we already have a in here and 2 times a here. We need to write h in terms of a, just kind of like the triangle that's directly above it. You see that I have a root 2a. That's kind of what we want to do here. Instead of h, I want something in terms of a. So go ahead and let's complete the Pythagorean that's in here now, right in here. 2a squared, that's 2 squared 4, a squared is 4a squared. And then subtract a squared from both sides. 4a squared minus a squared makes 3a squared is equal to h squared. Okay, now h is the unknown here, let's say, okay, assuming we know the value of a. Next we're going to do the principle of a square root, and the solution to h is going to be again plus or minus square root of 3a squared, which being in geometry we're just going to take the positive root, right? So h is going to be what? A root 3. The reason, because the square root of a squared is a, and 3 remains in the radicand. And we did what we want to accomplish. We managed to again write all 3 sides involve of some form of a. Okay. Now, let's take a look and see how we're going to apply this. First, I'm going to show you what's in the book with regards to this triangle. So this is what the book shows. Now, if you have a 30, 60, 90 triangle, then we are given if one side is a, that's one side a. The hypotenuse is twice that. And the altitude or height is root 3 times a. Okay, so again, we got some form of a in every side. Now, one way you can remember this one is if you put 1 in here, so you can kind of go, you go 1a, 2a, and 3a, put the square root on it. So this is what I'm thinking, 1a, 2a, and 3a, put the square root on it. Okay, sorry, I know this is sloppy, but you have the figure to the left. This is what I'm trying to clarify. Okay, so anyways, that's what this rule says. Okay, now again, the power of this triangle, special triangle, is that if I know just one side, I should be able to determine the entire triangle, the other two sides. So just to show you an example, if this is my 30, 60, 90 triangle, and suppose this is 5, that's all I need to solve the triangle. So if I try to use Pythagorean right now, I cannot directly because I have two unknown sides, right? So I can still do this using the knowledge of what we just found out here, right? This one. So first of all, the side opposite 30 degrees, see that's 30 degrees, that's the side opposite it. The side opposite 30 degrees is going to be half the hypotenuse, or hypotenuse is twice that. So here's my 30 degree angle side, and the side opposite that is this one, which is a 5. That's half of the hypotenuse, so hypotenuse must be 2 times 5, or 10. And see how that worked? And for the altitude of the triangle, right, the altitude or height, you just put square root of 3 on A. 5 acts as an A, so it's going to be 5 root 3. You see how I work this? We solved the triangle. We have all 3 sides figured out. Okay, now let's take a look at the exercises that are in the book involving 30, 60, 90 triangles. So let's take a look at number 32. In number 32, we have a 30, 60, 90 triangle that looks like this. We're given that's the 60 degree measure angle. The hypotenuse is 18. This is the right angle. We want to find the other two sides. So remember, this will be the 30 degrees because the one in front of it is 60. Now the side opposite 30 degrees is this side. That's half the hypotenuse, and in fact that is what A is. So A is half of 18, or 9. Okay, or what we can do is this. Let me remove these. What I can do is this. Match 18 against the hypotenuse, right? So 18 should equal 2A, and solve the equation. Divide by 2, we get A is 9. So however you do it, A turns out to be 9. A is the shortest side. And what is the altitude going to be? That's this part, right? And that is this side, the altitude. Remember, the altitude also gonna have A in it. True? In this case, right in here, root 3 times A. So root 3A, and of course A is 9. That's going to be 9 root 3, and we have solved for that side. In fact, we solved the whole triangle. We know the measure of all angles and all sides. True? And there we have this one. Okay, now let's try another one. Let's take a look at number 36. In number 36, we are given a triangle that sits like this. Okay, there's a 90 degree angle. This is the 30 degree angle. This is the 90. And we are given the altitude is 7. Right? And we want to find the other one. Remember, this is the hypotenuse. The hypotenuse always lies in front of the 90 degree angle, the largest angle in the right triangle. Okay, so let's work this one. Now, remember the altitude is root 3 times A. true. So we're going to, that root 3 times a is what 7 is right now. 7 is root 3a. So I can solve for a now. Let's divide both sides by a square root of 3. And there you go. That's the shortest side. That's a. This was root 3a. Oh, actually, no, I'm sorry. That's 2a. That's the hypotenuse, right? That's your 2a. The shortest side is a. And of course, for this one, the altitude is 7. That is altitude. That's given to be 7. That's how we came up with that equation. Now, let's rationalize the denominator. 7 over root 3, multiply top bottom by root 3, and it becomes 7 root 3 divided by 3. This is the form of the answer that you would expect in the book. Now, let's see. We found a hypotenuse, 2a. So hypotenuse is going to be 2 times a. I don't need parentheses. It's going to be twice a, correct? That means 2 times a, which is this right here, 7 root 3 over 3. And that makes it 14 root 3 over 3. And there we have solved this triangle. Okay. So, there you have it, just a few examples of these. And that's pretty much what we want to cover in this section. So remember, in this section, we talked about the general Pythagorean theorem. Let me scroll that to the top. There you go. So we talked about right in here, Pythagorean theorem. And then we discussed the principle of the square roots, which helps us solve for triangles down the road, like right in here in this example. This was an example of Pythagorean theorem. And then we looked at our distance formula. We derived the formula for an isosceles triangle, where just knowing one side enables me to solve for the whole triangle. And we looked at the second special triangle, the 30, 60, 90 triangle. And we're able to solve these directly from the formula that we have for both of those special triangles. And with that, we are done with this section.